All right, so yesterday we spent some time talking about these objects that we called on-shell diagrams or on-shell graphs. Just to quickly recapitulate, recall that the point is that for particles of any spin, the three-particle amplitudes are completely determined by Poincare invariance. If we're talking about gluons or supersymmetric gluons, it's all equally true. But the geometry of momentum conservation for three particles is such that either the lambdas are all parallel and the lambda tildes are generic, or the other way around. And associated with each one of these is, so there's two kinds of configurations we can have for three particles on shell. The one where the lambda tildes are all parallel and the lambdas are generic are the black vertices, the other way around are the white vertices. And we associated these in the supersymmetric theory with the k equals 2 and the k equals 1 amplitudes. These are completely fixed by, again, by Poincare and by super Poincare invariance in this case. And then we just started, we decided for fun in the beginning to start exploring the objects that we can get by taking these three-point functions and gluing them together. Where gluing them together means putting them together in pictures like this. They don't have to be planar, although we're focusing on the planar problem. And just integrating over the on-shell phase space of all of the internal lines, summing over all the helicities, or more conveniently in the supersymmetric case, integrating over the Grassmann on-shell parameters, the eta tildes, for all of the intermediate lines. So these are some nice objects. They're nice canonical kinds of things that you can do on shell. As I stressed yesterday, they're not Feynman diagrams. They're all the internal lines, everything there is on shell. We're just integrating over them. And towards the end yesterday, we actually went through the logic for why these things are actually much more than academic interest. We can actually use them to completely directly determine the amplitudes for the theory, just a tree level, but to all loop order in a completely consistent way, in a completely systematic way. And there's a physical novelty in this way of thinking about things, which is that it is indeed possible to represent all the things that normally in quantum field theory we associate the words virtual particles, loop momenta, off-shell. None of those things are actually necessary. Everything can be completely captured by these on-shell diagrams. So, so the purpose today is to try to understand what these on-shell diagrams really are, how to compute them, what their invariant content is, and how they lead to a picture of the physics of scattering amplitudes in n equals 4 superhang mills, where all the symmetries of the theory are trivially manifest. Okay? Again, that, yes? Yes. Right. Yes, yeah, so as we said yesterday, already tree amplitudes, this was a 4-particle tree amplitude, seems to have a loop in it. So in this story, loops are, I mean, you have to draw loops, okay? But the correspondence between what you normally call loops and loop order here has a very simple, is very simple. I mean, it has to do with the number of free integration variables that we said last time is the number of faces of this graph, of these graphs, -1. Okay? So as I said yesterday, the sort of main physical idea behind this whole approach is to concentrate on these on-shell diagrams as a central object of study. This will now be associated with these wonderful structures in algebraic geometry, which I will describe today, which taken together also make the conformal and dual conformal symmetry and really directly the Yangian symmetry of the theory completely obvious. Okay? So that's something which is impossible with a conventional Lagrangian description. We can have infinite fun, and it's extremely important and good to know that there's one object that in one space-time you can call a scattering amplitude, in another space-time you can call a Wilson loop. This is wonderful, but either one of those descriptions is making a commitment to one description or the other and obscures seeing all the symmetries. If you want to see all the symmetries, it's inevitable that there has to be a non-space-time based description, and that's exactly what we're going to see. Okay? And what? Yes. Yes. No. I don't think so. No. I mean, we haven't done it, but I see no obstruction to carrying it out for any general quantum field theory, right? Okay. Okay, so that's the just to say one amusing thing about this about the mathematical structure is that it is a subject which has been completely coincidentally explored by the mathematicians in the last 5 to 10 years or so. So for no apparent reason at all, as far as I can tell, these structures have been studied by the mathematicians quite recently. And in fact, some of the specific structures we're talking about were almost seen simultaneously. And we happily started talking to them. Of course, they knew things about this object we didn't know about. We knew things about the object they didn't know about, but n equals 4 super Yang-Mills knew more about the object than all of us. And so it's been tremendous fun figuring out how to think about it from the point of view that physics wants to think about it, which of course not only gives us lots of insights into the physics, but also gives a rederivation and a generalization of a lot of these things that they've discovered relatively recently. Okay.
All the conventional diagrams in quantum field theory, like say the backward diagram, like you
yes.
would have a way of drawing here as well.
So far, I'm just talking about computing. Let's just. I'm talking about computing on-shell scattering amplitudes. Okay. Towards the end, I will talk about how I think these things might, more speculatively, how I think the same kind of ideas might be used to determine form factors, correlation functions, and so on. But so long as we're talking about on-shell scattering amplitudes, for n equals 4 super Yang-Mills, the claim is that you can get all of them in this way. The hope is that you can get all of them for any theory. All right, but let's actually begin by. Let me also remind you of something else. So, so we noticed two equivalences already thinking about on-shell diagrams. There's a rather trivial equivalence that anywhere you have collections of black vertices, you can collapse and re-expand them any way you like. And there's this really non-trivial equivalence, even though it was extremely simple, but this, as I said yesterday, is going to be a big star of the show from many points of view. This thing called the square move, that everywhere you see an on-shell diagram like this, with this little square, you get to reverse the colors. So this is the... No, it doesn't have to be external. This can be anywhere inside. Yeah.
The external assignment of numbers is the same.
Yes, of course. Yeah, that's right. That's right. But this could be just inside the graph anywhere. Okay? Yeah. So you can call this the merge-unmerge move. Okay, and that means that there isn't a unique representative for the objects that we're talking about. So let me just give you an example. These two on-shell graphs, there are two on-shell graphs for 6 points. And if you stare at them, it's not obvious. Are they the same? Aren't they the same? But in this particular case, there's a sequence of square moves that can take you from one to the other. Okay? So already, even at this very primitive level, there's a question. If I hand you two different graphs, how do you know they're the same? How do you know, how can you decide whether they can be related by a sequence of square moves and so on? Each graph by itself is not invariant. It's a representative of something. The question is, what is the invariant content? And how do you read off the invariant content from a graph, and how do you characterize it, compute it, and so on? So that's what we're going to do. Now, it turns out that the invariant content to all of these things is actually a permutation. There's a way of associating a permutation with these pictures that we'll talk about in a second. And this permutation is actually the core. This new way of thinking about permutations is actually the backbone on which this entire subject is built. But before describing how it works here, because I think it's both nice and physically important, I want to remind you, this is of an begin by reminding you of an earlier manifestation of this link between permutations and scattering, which is between permutations and scattering amplitudes in integrable theories in 1+1 dimensions. Okay? So let's say we have some permutation, I don't know. Okay? If I just give you a permutation that doesn't look much like physics, I mean, scattering amplitudes are fairly sophisticated functions of external momenta, and the particle labels and the helicities. But if you strip off almost all the physics, you're just left with the labels. And the closest, the only combinatorial analog you could have to a scattering amplitude is a permutation. Okay? It's the only change you can make just on the labels. So this doesn't look much like physics, but we can start making it look like physics by representing this permutation graphically. Okay, so 1 goes to 5, 2 goes to 3, 3 goes to 4, 4 goes to 2, 5 goes back to 1. Okay. So now we've, I could have drawn the lines more straight, but now we've represented this permutation in a way that allows us to interpret it as a scattering process in 1+1 dimensions. Okay? So we think of it as 5 particles starting in the infinite past, undergoing 2 to 2 scatterings, and ending up in the future. Okay? Now, of course, this is very familiar from integrable theories in 1+1 dimensions. That's exactly the point, that the fundamental interaction is the 2 to 2 interaction. And furthermore, if you now really want to associate with physics, so you want to actually put little 2x2 scattering matrices at each one of those vertices, if you really want to insist that the only thing that matters is the permutation and nothing else, then, oh, I should say one more thing. Of course, drawing such a picture is not unique. There's lots of ways of drawing a picture like this. Each one of these pictures corresponds to one particular way of breaking a permutation up into a product of adjacent transpositions. Okay? And when you break up a permutation into a product of adjacent transpositions, the order in which the permutations take place is just translated into the time ordering of all these different 2 to 2 scattering processes. But again, if you actually want to build a physics theory associated with this, it needs to satisfy the basic Yang-Baxter move that tells you that all that matters is the permutation and nothing else. Okay, so that's what guarantees that all that matters is the permutation. So this is already a very old, very beautiful story that links, ultimately, the invariant content is just given by permutation. You hand me a permutation, that tells you everything about the scattering. All these different ways of drawing the diagram are equivalent. They give you the same answer. There are also completely useless things you can do in the diagram that don't actually change the answer. For instance, if I have that, I can just replace it by that. So the diagrams are normally not unique. We can add all sorts of extra loops if we want. There's all sorts of extra irrelevant stuff. But even the diagrams that have a minimum number of loops aren't unique. There's lots and lots of them. Okay? So this should start sounding a little familiar, but we're going to see much more concretely. What's going on? All right, so This is an old story. Many people have wondered. I mean, just speaking for myself, when I was first starting to think about scattering amplitudes, I wondered, why isn't there some analog of this story in higher dimensions? But it seems impossible because there are many aspects of this story that are intrinsically one plus one dimensional. First of all, there's no particle creation or destruction. You start from the infinite past and you go to the infinite future. And related to this, it's the fact that everything is on a line that allows it to be possible that only 2-to-2 interactions are what matters. In higher dimensions, there most certainly is particle creation and destruction, so much so that when we talk about the scattering amplitudes, right away, without even saying it explicitly, I mean, I didn't say it explicitly, but if you think about it, it's kind of remarkable that we do this right away. The whole matrix interpretation for scattering amplitudes, past to future, we instantly erase by using crossing symmetry to make all the momenta outgoing. Okay, so we have the picture of scattering amplitudes we talk about is not a bunch of things go to a bunch of things. It looks like vacuum goes to end things going out, for example. Okay, so that looks nothing like that. And related to that, the fundamental interactions are 3-point and not 4-point. Okay? Okay, but if we nonetheless try to press on and see what kind of connection could there possibly be between permutations and scattering in higher dimensions, one inspiration we can take from this 1 plus 1 dimensional story is that it has to involve completely on-shell processes. Okay? This is not a statement about individual Feynman diagrams contributing to this that they're associated with permutations. It's the actual completely on-shell description of the physics, which is the thing that's associated with permutations. So this is now in 3 plus 1 dimensions, we're talking about on-shell processes, and they look like this. Graphs where you have n particles on the outside with black and white vertices sewn together. So one should try to associate permutations with a picture like this. Now, but again, let's forget about the physics and just come back to seeing if there's another way of thinking about permutations where the particle labels are out on the outside, let's say, of the boundary of some disk. Okay. And quite beautifully and simply, there is. Okay, so let me first describe it in the simplest case, the simplest non-trivial case of 3 particles. So the non-trivial permutations here are like 1 to 2, 2 to 3, 3 to 1, okay, or the other way around. So let me describe how I'm supposed to read off that permutation from this picture. So I'm going to associate that 1 to 2, 2 to 3, and 3 to 1 permutation with this picture. How do I find the image of 1 under the permutation? The rule is you walk into the graph starting from 1, and if you encounter a white vertex, which is the only thing we have there, you make a left turn. Okay. That gives me 1 to 2, 2 to 3, and 3 to 1. Okay. And if you want to do the other one, you make a right turn. But now with this rule, I can glue these things together in more complicated ways, like those pictures, or like this picture. So here you can see what is the permutation. It's 1 to 3 going left and right, 2 to 4, 3 to 1, 4 to 2. Okay? So that little square is associated with that permutation. Actually, it's obvious that if you glue together any set of white and black vertices like this, that if you start from the outside, you end up on the outside somewhere. It's like a maze. Okay? if you follow the left-right paths, you end up outside somewhere. And also that no two guys on the outside can go into the same one at the end. So every such picture does give you a permutation. Okay? So in that direction, it's totally obvious. Every such picture gives you a permutation. What's not obvious, yes? Huh? Here it's completely tied to here it's completely tied to a planar graph. If you had non-planar graphs, you would start talking about not just the permutation associated with the path, but its windings around any non-trivial cycles you might have. Okay? But let's just stick with the planar graphs for now. Okay. So it's obvious in one direction that any graph like this gives you a permutation. What's not obvious is that every permutation can be represented by a graph like this. Okay? And that's something that was actually proven by Dylan Thurston, the son of Bill Thurston, back in 2004. So, and with a very nice constructive proof, but still, I mean, it's one of these complicated looking mathematical constructions. This is one of many things we're going to give a much more transparent understanding to. So in 10 minutes, I will tell you how to build a graph like this for corresponding to any permutation from a point of view that's obvious to a physicist. But before doing that, I need to tell you a little bit more about what kind of permutation this is, because these things are actually slight generalizations of a normal permutation. The reason we have a natural generalization of the notion of a permutation is that we have a cyclic ordering of the guys on the outside. So 1 to 2, 2, 3, 3, 4, and so on. And so it makes sense to talk about the following. It makes sense to always imagine that the permutation of a label always goes to its right. Okay? So I have 1 to 3 is fine, 2 to 4 is fine, but 3 to 1 is jumping back. 4 to 2 is jumping back. Okay? So we always are going to make it so everything is moving forward. So instead of writing it like this, I'm going to write it as 1 to 3, 2 to 4, 3 to 5, and 4 to 6. Okay? Because I have 4 labels. Okay? So this is it's a decorated permutation, an affine permutation. It has many different names, but its A goes to sigma of A, where sigma of A is just defined to be greater than or equal to A and less than or equal to A plus n, and where sigma of A mod n is a normal permutation. This is an affine permutation. Now, with an affine permutation, there's one more label, not just n, but roughly the number of times you jump back. Okay? I mean, you can have a permutation with just 1 to 2, 2 to 3, 3 to 4, 4 to 1, where you just jump back once. The number of times you will jump back. That's another integer, k. So we have n, and there's an integer k, which is the number that jump back. Loosely, and concretely, k is just the average value of sigma of A minus A. Okay? If you didn't jump back at all, that average value would be 0. And of course, since sigma of A is a permutation, except for some number of guys, k of them, you jump back. For the one that you jump back, you add n. And so this sum is guaranteed to be an integer and is actually equal to the number which jumped back. Okay. All right, so this should start looking better if you're an amplitude person, because now these permutations are associated with 2 integers, n and k, exactly as the amplitudes and on-shell diagrams and everything else. Yes? Huh? No, it's the other way around. So you give me a so this is the really fundamental object, is sigma. So you give me any you give me any mapping that satisfies this, and that's n. That is n affine permutation. Actually, the only place where the permutation doesn't determine it is in cases where either 1 goes to 1 or 1 goes to 1 plus n, for example. Okay, So those two. If you don't have situations where someone is mapped to itself under the image, then it's just exactly the same as the permutation, just the guys that jump back. But it does also help distinguish the cases where 1 goes to 1 or 1 goes to 1 plus x. Okay. All right, so these graphs are actually associated with these affine permutations. And it is possible to represent, any diagram in terms, it's possible to represent any permutation by one of these diagrams, and I'll show you how in a moment. But let's just say a few more things about this.
Yeah. Any permutation, are there any different sigmas that map to that same permutation?
No, you can have many, many more because of this, yeah, that's right. Yeah, so really the sigmas are the fundamental thing. Okay, so, but just some general comments. Obviously, there has to be some enormous redundancies here. First of all, I can draw diagrams with an infinite number of faces, and I have a finite number of permutations. So there has to be a notion of a reduced graph, a graph with the smallest number of faces that can represent a given permutation. So first of all, so there has to be some notion that in general, the vast majority of the faces are irrelevant. You can get rid of them and focus on the smallest diagrams that can give you a given permutation. Okay, but secondly, even when you have that, even when you have the most minimal, the smallest number of faces, there are still redundancies. And we can see the redundancies already here. For instance, if I take, not just for instance, if I take, you know what I'm going to draw, if you take this square and the square of the opposite colors, they give you exactly the same permutation. You just go around the square in opposite orders. Okay? So two diagrams that are related by the square move give you the same permutation. Is that clear? You know, right, right versus left, left. You get exactly the same permutation. Furthermore, if you're given something like that, then the permutation is right. Okay? But that's exactly the same as you would get from that. Just trivially, right there, for example. Okay? So we have things that are equivalent under the permutations, which are happily exactly the things that leave the on-shell diagrams invariant. Okay? Huh? And no more. Okay. So that's how you can decide whether these two diagrams are the same or not. You don't have to sit there doing all these square moves. You just follow the left-right paths and see if they give you the same permutation. Okay? So, you know, left, right, left, right, left. 5 goes to 2. Okay? Right, left, right. 5 goes to 2. Okay? They're exactly the same. So this is starting to get a little more interesting. All right. Yes. Yes. So the claim is that for the diagram with the minimum number of faces, which represents a given permutation, then all the different ways of relating them to each other are given by just leave the permutation fixed. The permutation is the only thing there is, and what generates all the equalities are just this square moves and this more trivial merge unmerge operation. I said this merge unmerge is really trivial. What you really should do is use it to make the graph bipartite. So you can take all the blacks and whites and glue them together, but I prefer to leave them like this because it reminds us of the underlying origin. Yeah.
You said this, but what does K map to in the graph?
Oh, so K maps. I didn't tell you. Well, I defined K last time for the graphs, but K in these graphs is in the scattering amplitudes, things are labeled by N and K. If you do it supersymmetrically, they're functions of some Grassmann variables, and it's the number of these Grassmann variables that occur in the expansion of the amplitude. It's the number of negative helicity gluons. And in terms of the graphs, there's many definitions, but it's the number of white plus twice the number of black minus the number of internal edges. Okay? Okay, but it's some integer between 0 and n. Okay. So every single aspect of this story has a mirror of importance for the amplitudes. It might bother you that we can draw these diagrams with more and more and more loops, more and more faces. And as we discussed last time, the representation of the loop integrand comes from exactly the things with more and more faces. Okay? In a very specific and concrete sense, all of the irrelevant variables that we get rid of under reduction are the loop integration variables. Okay? So all of quantum corrections is actually buried in the part that eliminates these irrelevant variables and leaves you with the basic ones. Okay? This also tells you that that last step of reduction is what I mentioned also before, that you can take this bubble and replace it like that. Okay? And that's what allows you, so the underlying picture is that you start with an arbitrarily complicated graph. It's in general not reduced. That means that via sequences of square moves and merge-unmerges, you can isolate these bubbles. You eliminate the bubbles as you go along, and you eventually come to a finite graph. And there's a finite number of these objects. So this is the first intimation of some massive simplicity in the structure of these on-shell diagrams. They appear to be arbitrarily complicated, but in fact, there's a finite number of them, and in a concrete sense, I mean, it's not like the information about all this stuff isn't relevant. It's actually relevant in determining the loop integrand in a very beautiful way. But the core of these on-shell diagrams is actually there's a finite number of them, and the finite number is in one-to-one correspondence with these affine permutations. Okay, so we could spend a while doing. Yes. Yes. Yeah, hold on. So I'm just about to make a comment about this. So it's important to note that this reduction does not keep the permutation invariant. Okay? There's another reduction that you would do that would keep the permutation invariant. This is also something which reduces. We'll see in a moment that these diagrams are associated with a point in the Grassmannian. And that's the association that arises from actually trying to compute the on-shell diagrams. This reduction is trying to keep the point in the Grassmannian fixed. Okay? But in the end, it is still true that the point in the Grassmannian that you end up with is characterized by the diagrams with the smallest number of faces, which are classified by these permutations. Okay. Before going further, I just want to make a little comment that this new way of thinking about permutations contains the old way of thinking about permutations as a special case. Okay. So the Yang-Baxter story is a special case of this story. And in fact, this is a more atomic and simpler explanation of where the Yang-Baxter move comes from. So let's talk about how that is. Well, first of all, how can that be? You know, I draw a picture like that, say. Here I have these 4-point vertices. The underlying things, there's no basic 4-point vertices here. So in order to make a connection, I need to tell you how to interpret these pictures in terms of the new diagrams. Okay, so, and of course here I used to label them 1, 2, 3 and just 1, 2, 3 up here, but let me put a 1 prime, 2 prime, 3 prime. After all, these are past and those are future, so that makes sense. So one way I can blow this up is to take this, and everywhere I see that, replace it with that. Okay? Right now I'm just doing things at the level of the pictures. if we ever get to it, when I actually tell you how to build points in the Grassmannian and matrices and so on associated with this, we can do it also at the level of matrices, and everything works perfectly, of course, as it should. But just so you see at the level of pictures. So what happens to this picture? Well, this picture now looks like this. Okay? So I've blown up each one of the 4 particle vertices like that. Okay. Now, the Yang-Baxter move is like a big move. You take this line, you move the whole thing over. Okay? But we're now going to see that it follows directly from our little simple local moves. Okay? So first, let's merge and unmerge this guy. Okay. Next, let's do the square move on this guy. And finally, let's merge and unmerge that guy. And so that is nothing other than that. Okay. So you see, instead of trying to find something 1 + 1 dimensional in here, it's really the other way around. The 1 + 1 dimensional story is a little special case of this more general way of thinking about permutations. In fact, having seen this, there's one other so Yang-Baxter is inside this story then. Okay, so Yang-Baxter is inside the story of so 1 + 1 dimensional Yang-Baxter is inside this 3 + 1 dimensional story. Yeah.
Yang-Baxter equation
Yes.
implies integral difference.
Yes.
So are you restricted to a set of variables in 1 + 1 dimension?
Well, of course. Here, yes, that's right. So here, all I'm saying is that this old picture for scattering, the old picture of permutations, is contained in the new one. Okay. But notice something interesting. You see. There's something quite vivid that these pictures do not have, that the Yang-Baxter picture has. There's no notion of time. There's no notion that you start from somewhere, you go from somewhere. If anything, there's a notion that you start from nothing and build up and build up the graph. We'll come to that picture just in a second, because thinking like that is going to tell us the correct way of building up these graphs. But in the special case where the graphs are arranged so that you can give them this temporal interpretation, for those graphs, the Yang-Baxter move is a special case of the things that we have. But I want to mention now, there's one other special case. Yes?
The move that you, the first thing
Yes.
connect the 4-point thing to the black-white dot.
Yes.
What is the motivation for that?
Sorry.
The first
Here. Oh, it's just that I'm trying to see, can this picture be embedded in what we're talking about? We don't have 4-point vertices. We just have 3-point vertices. Okay?
So if you do that,
Okay. Yes. So all I'm saying is that if you take any picture like this, it's a special case of the pictures that we're talking about where you blow up the vertices in that way. And then, interestingly, if you now forget about that, just treat that according to our rules, the Yang-Baxter move follows trivially. Okay? From this, I hope you see it's interesting. It's something much more local, and atomic is like moving this whole line over. Okay, but yes.
So just in the dark and white circle there, there is no concept.
Sorry?
When you are getting the fourth one,
Oh, sorry. So let me say. So I should have said something here. So when I do this, notice what does the permutation look like? Here, 1 goes to 2 prime, 2 goes to 1 prime, but 1 prime goes back to 1, and 2 prime goes back to 2. Okay. So in this way of drawing it, there is an asymmetry. The permutation up, for the left-right paths up, is the same as the one here, but here too, I didn't draw the arrows, but everything is moving up in time. Okay? And we don't even talk about the one down. The one down is trivial. Okay? But that's exactly what lets us think of another generalization. After all, you could have said, look, it's very simple. to associate, to generalize something like Yang-Baxter to higher dimensions, where everything is out on the boundary, you just have to have an even number of particles. If you have an even number of particles on the boundary, then we can draw pictures just with 4-point interactions that can look like this, for example. Okay? So imagine this is some putative theory whose scattering amplitudes we're calculating. And we might imagine having sort of on-shell diagrams like this, where these are fundamental 4-point vertices. And how could I associate a permutation to it? Well, I could just say it's like 1 to 4 and 4 to 1, 2 to 5 and 5 to 2, 3 to 6 and 6 to 3. Okay? If you have an even number of particles, you can put half of them at the bottom, half of them on the top, connect them any way you like, and then put them all on the boundary of the disk in this way. Okay? Okay, so this is another way of associating permutations with scattering. How could we realize this picture in terms of our graphs? We can realize this picture in terms of our graphs by blowing up these guys into a little box. See, this is a permutation which is exactly symmetrical. Okay? And what do these correspond to? This also has a name in physics. This is the ABJM theory. ABJM has fundamentally the 4-point vertex. And the entire story of scattering amplitudes in ABJM theory is also a special case of what we're talking about, where you blow up the vertex in that way. And also, if you want to know about equivalences between different diagrams in the ABJM theory, it's just given by Yang-Baxter moves locally. Okay? It's just any two diagrams that give you the same permutation are actually the same from the point of view of on-shell graphs. So we have this fascinating hierarchy that every single one of these integrable structures that we've run into, Yang-Baxter in 1 plus 1, ABJM in 2 plus 1, N equals 4 super Yang-Mills in 3 plus 1 are actually associated with a new picture for permutations. And the interesting thing about this new picture for permutations is that time isn't playing a special role in the way you would think about it. Instead, it's these glued together diagrams with black and white vertices. Okay. Yes. Yes, and in fact, people had noticed this. People had noticed that there's exactly the same kind of Grassmannian structure in ABJM as there in N equals 4 and so on and so forth. But now, I mean, there's antecedents for all these things. I said in the beginning, I'm not going to reference everything as we go along. It would make these talks 1.5 times longer than they already are. But yes, but the fact that all these things are sort of unified in this way of thinking about the combinatorics is new and interesting. Yes. Yeah.
I mean, so in these 1 plus 1 dimensional integrable theories, that means there is some Grassmannian way of formulating them?
Yes.
That's not that's already known?
Actually, this fact was one of the things that got one of our collaborators, Alex Posnikoff, into this business. Okay? So yes, this connection is something that was known. This one is new, but and you know, I'm sorry, it's really going to be impossible to say all the things that maybe need to be said. But there's many different. There's 3 different theories of positive Grassmannians. There's the most general theory, which is the one I'm talking about. There's 2 special cases, and the 2 special cases correspond to the null Grassmannian and just the oldest theory of positive matrices that goes back to the late 1800s. The oldest theory is Yang-Baxter. The null Grassmannian is ABJM, and the general positive Grassmannian is N equals 4 super Yang-Mills. Okay. But let's keep going and think about the most basic things that you might want to do. Just from the permutations, what's the most basic operation that's important for permutations? It was as important before for the Yang-Baxter's, for the 1 plus 1 dimensional story as well. The most basic and fundamental operation involving permutations is the adjacent transposition. If you know how to do an adjacent transposition, you know how to do everything. Okay, so what does the adjacent transposition look like in terms of these on-shell diagrams? Let's say I gave you some diagram that represents some permutation, and I want to do an adjacent transposition where I transpose n and 1. So I want to have a new permutation where n and 1 are transposed. Well, all I have to do is add a little black vertex there and a white vertex there. Okay. See, whatever it was that was going into n, I go right, left, and it goes into 1. Whatever was going to 1, I do left, right, and it goes into n. So this operation of adding a little bridge, from the point of view of the permutation, is doing an adjacent transposition. And it's clearly a fundamental operation from the point of view of the combinatorics. Of course, yesterday, this is what I described to you as a very important fundamental physical operation on on-shell diagrams. This is adding the BCFW bridge. Okay? So BCFW is doing an adjacent transposition on the permutation. Okay? But now we can be inspired even purely from the combinatorics to do something. Yes.
So far, you're associating permutations with on-shell diagrams, the lowest possible number.
Yes.
This will not keep that in various.
Yes. So exactly, and the one tiny thing that I'm going to talk about in a second is what guarantees that it's going to do that. Okay. But yes, for the ones that keep keep it minimally fixed, then right. Okay. So what we'd like to do is mimic what for ordinary permutations is the fact that you can build up any permutation by product of adjacent transpositions. Okay? So now if someone hands me any affine permutation, I should be able to build it up as a product of adjacent transpositions. And if I can, that's going to immediately tell me a way of building the graph. Okay? There's one small subtlety associated with the fact that it's an affine permutation, which is that the bottom permutation, the trivial permutation, what is the trivial permutation, right? It isn't just 1 to 1, 2 to 2, 3 to 3, because that's k equals 0. That's fine for k equals 0. For general k, I have n choose k different possible bottoms that I could have, corresponding to which ones are mapped to themselves and which ones are mapped to themselves plus n. And in the language of these on-shell diagrams, a guy which is mapped to itself is represented by a little lollipop with a black vertex, and a guy that is mapped to itself plus n is represented with a little lollipop with a white vertex. Okay. So we have a number of different trivial permutations. For example, this is one trivial permutation which has k equals 2. All right. Okay. And it's really just taking care of the affineness and this k, which makes this just one twist more interesting than just the trivial case. And it's, I think, probably why it wasn't done in the math literature before. So you'd think, I mean, this is the most obvious way of building up a graph, but it's not quite a normal permutation, so there's this small subtlety that you have to deal with. If sigma of A is less than sigma of B, so there's some ordering. So if sigma of A is less than sigma of B, you're allowed to transpose them. Okay. Other than that, otherwise, and we only want to transpose adjacent guys. So adjacent means that either A is next to B directly, or they're allowed to be separated by any number of guys that are mapped to themselves or mapped to themselves plus n. So anything which is mapped to itself or itself plus n, you just forget about. You treat everything around it as adjacent. It'll become clear from the picture in a moment. Okay? So let's see how I would decompose this into a product of adjacent transpositions consistent with those rules. Huh? Yes, yes. A is smaller than B with all C between A and B if there are any, satisfying that sigma of C is equal to C or C plus N. Okay? Okay, now there's many, many ways of doing it, as always, but we can choose one particularly nice one, which is that as you go down, and the very first time you encounter this, you just do the transposition. Okay, so that's the rule for when to do it. So as we go down, what's the first time sigma of A is less than sigma B? It's right here, so I transpose them. 4, 3. So this stays 5, that stays 6. Let me remind myself that I transpose 1 and 2. Then here, what's the first time? It's here, so I can do 2 and 3. So that's 4, 5, 3, 6. Now notice something nice happened. 3 has gone to 3, so this is going to be frozen forever. Okay? We're never going to touch it again. Now I keep going. What's the first time this happens? It's 1 and 2 again. 5, 4, so that's good. 1 has gone to 5, frozen forever. And here, what is the first time? Well, it's now at the bottom, so I'm going to do, sorry. Oh, sorry. No, I just wrote it down wrong. Okay. So we did 1 to 2, then we did 2 and 3. So sorry. 2 and 3 puts a 3. Oh, sorry. Let me erase this column. Okay. So we transpose 3 and 4, that's that. The next two that we can transpose are 2 and 3, so we get that. As I said, now 3 is stuck forever, so I'm not going to touch 3 again. The next time I can transpose them is 1 and 2 again, so that's 5 and 4 and 6. Now 1 has gone to 5, so I'm not going to touch that again. So the final thing is 2 and 4. Which puts that to 6 and that to 4. Okay? And now I'm done. Now something has gone down to the trivial permutation. 5, 6, 3, 4. Okay? So I've broken the permutation up into adjacent transpositions. So let's now draw the picture. So the picture really is, you start from the vacuum and you build up the outside. The vacuum is one of these adjacent, yes? No. That any C between them, if there are any C's between them, they have to be C or C plus N. You have to skip over all the guys which are on the inside. Okay. So let's see how this works. So here I have 1, 2, they're black, 3, and 4. Okay. So that's the vacuum, and I start doing it. So I have to put a bridge between 2 and 4. Let me put this a little smaller here. So putting a bridge between 2 and 4, putting a little black dot here, a little white dot there. Now, a little rule in these pictures is that any hanging lollipop you get to erase. Okay? So only if it goes all the way out to the boundary. Otherwise, anything in the middle, you just trivially get to erase. And furthermore, any dot that's just on a line, you also get to erase. So these are some extra trivial rules that I didn't tell you explicitly, but things like that. Okay? So what has happened here is that I've just connected 2 and 4. Okay, so next I have to connect 1 and 2. Black dot, white dot, erase lollipop, erase white dot. Next I have to connect 2 and 3. So let me draw this already a little more like that. I have to connect 2 and 3. Black dot, white dot, erase lollipop, erase white dot. Okay. And finally I connect 1 and 2. Black dot. Well, so let me already draw this one a little more nicely. Connect 1 and 2. Black dot, white dot, and we have recognized our friend the square. Okay? So these pictures, each picture like this corresponds to the exact analog of the Yang-Baxter story of building up a permutation from product of adjacent transpositions, but there's no time. Okay? It's instead a picture of starting from nothing and going out. And okay, so I gave you the concrete rule now. How do you build a graph for any permutation? Okay. Simpler than Thurston's rule. Okay, so I'm doing really badly for time. Okay, this is very interesting. Okay, so that's it for the purely combinatorial part of the story now. Okay, so we've seen that that there's a natural way of associating permutations with these graphs with black and white vertices. The basic equivalences are exactly the things that leave on-shell diagrams invariant. So, and the things that are important for the on-shell diagrams, like the BCFW bridge, are important for the permutations. And we have this BCFW bridge decomposition for any on-shell diagram, which has this interpretation of starting from nothing and building up the configuration as you move out towards the boundary. So far, this is all pure combinatorics or graphs, things like that. This is already useful if you want to play with on-shell diagrams and decide, hey, is some diagram, is this the same as that? Check to the left, right path, okay? It's also useful if you want to know, this is also interesting, so let me tell you a few more things. So you see, the diagrams, as we think about them in physics, are built locally, okay? But because of all these equivalences, their invariant content is global, okay? So you can't decide locally whether two diagrams are the same or not. You can decide about the invariant content by global things, which are given by these left-right paths. So how can we decide, for example, something else which is very important in general, how do we know whether a given on-shell diagram is reduced or not? How do we know that it doesn't have secretly lots and lots of extra faces? Well, there are a number of ways. There's one which conceptually looks the prettiest, and there's one that's actually the most computationally effective. The one that's conceptually prettiest is the following: that a diagram is reducible if here's the left-right path. Okay, they're all zigzagging along, but I'm suppressing the zigzags. And here's the left-right path. If they have a double crossing like this, if they have a double crossing, then the graphs are reducible. Okay? Again, very analogous to the Yang-Baxter story. That thing is crap. You can just you can undo it. Okay? And in fact, more than that, you know which part of the graph all the action is going to happen in. You just have to look at the part of the graph that's contained in there, and it's possible to do square moves and merge unmerges to isolate a bubble. Then you can remove the bubble. Okay? So the bubble itself is very degenerate, but it's an example of exactly that phenomenon. Okay? This path and that path exactly double cross in that way. Okay? Another way that you can check, if you don't want to stare at all these left-right paths, another way that you can check whether a graph is reduced is to take the permutation you got from the graph, forget about it, take the permutation, then decompose into a product of adjacent transpositions, okay, in this way. There's some number of steps that takes. That number of steps must match the number of faces of the graph, -1. Okay? If the graph is reduced, the number of steps is the dimensionality of the configuration, which is the number of faces -1. So if it doesn't match, you don't have a reduced graph, and you should go and reduce it. Okay? So whether graphs are the same or not, whether they're reduced or not, are purely functions of this global information. So far, yeah.
Always a three-level graph in the original.
No. In fact, no. You see, you should notice that nowhere in these pictures am I actually using the fact that I'm in 4 dimensions. This is just about these. This is just about black and white vertices. Okay? And this is actually going to be the case. The entire story that we're talking about is suited to describe, if you like, invariance of or even Yangian invariants of the supergroup SLM/M. The particular case of 4 dimensions is SL4/4. But actually, 4 in this story plays very little role. Okay? So this is these are really purely, so it does not in general correspond to tree diagrams. It's a very interesting thing about the whole picture. There's no distinction between trees and loops. You know, I mean, there's some distinction, of course, but they're very, very mixed up with each other in this way of thinking about things. Yes?
So, I mean, once I give you a permutation, you reduce the graph completely, and that just gives you either a tree or a loop, and that's it. There's no, I don't need to add loop information apart from giving you a permutation. Is that correct?
Well, so if you want to represent the permutation, there's a graph with a fixed number of loops which does it. Okay? Now, what that corresponds to in the physics, is it a tree amplitude? Is it a unitarity cut? Is it a loop integrand? What is it? It depends on the particular question you're asking. Okay. So, but one thing which is true, I've said it a number of times, but it'll become clearer as we now start making connection with physics and not just with combinatorics, is that the vast majority, I mean, asymptotically at high loop order, all the loop integration variables are these irrelevant bubbles. And this is actually a very powerful way of thinking about things, because in a moment I'll describe that there's a form associated with all of these things, that the on-shell diagrams are associated with a form, and these reductions correspond to just factoring out of the form d log of certain variables that never play a role again. So as you're going along, you reduce a graph, there's a d log, you just take it out, you keep going, you reduce another thing, you pull out the d log, you pull out the d log. In the end, you have a ton of d logs. In fact, everything is going to be a d log, but including the ones that survive. Everything is a d log. But as you're going along, you strip off the irrelevant ones. D log, I'll never see you again. D log, so you throw them all to the side. Okay, you're left with something at the bottom, which we'll talk about how to calculate. And now this object, yes.
For physical amplitudes, you
Yes.
need to know what the d logs are. Right?
Yes, right. But we know that's exactly what we're going to see. Okay, so all these things we know exactly what the d logs are, and that's what's powerful about it. You don't have to, as I showed you as I showed in the example yesterday, if even that simplest 4.1 loop guy turns out to be 4 d logs, but if you start long enough, maybe you'd be clever and recognize it as 4 d logs. Doing things this way, it's handed to you as a 4 d logs, and not just in some abstract way that you then have to go find it yourself. It just exactly gives you in your hand precisely the form that does that. Okay. Yes.
I mean, in some sense, the permutation contains information about the amplitude.
Yes.
You're saying that for n particle amplitude, you don't have more than n factorial number of independent trees.
That is actually correct. That is actually correct. Yes.
Which is very surprising.
Yes, it's very surprising. But this is the statement that I mean, of course, there's the loop integrand. So, but this is the thing that let me say it in a more familiar language. There are a finite number of leading singularities. Okay? So you have a finite number of objects that sort of sit in front of all these integrations. That's a very surprising statement. It's not obvious at all ahead of time. In fact, there was one of the, when we first ran into the structure in the Grassmannian, I haven't talked about Grassmannians yet at all, right? But when we first ran into the structure in the Grassmannian, that was the most surprising thing about it. There was no loop order in it anywhere, and yet the claim was that it contained all the leading singularities. So there had to be a finite number of leading singularities. That was the conjecture. Okay, so it's true. I mean, all those things are now really simple to approve from these pictures. But yes.
Which or beyond a given loop order,
Yes.
everything is true.
Yes. Beyond it.
Formula for that? So for n particle, or how many?
Yes. Yeah. I mean, it's not a very simple formula I remember off the top of my head. But yes, for any. In fact, it's even more dramatic than that. Because, for example, if you're talking about n squared MHV amplitudes, okay, let's say, just to give you if we're talking about NMHV amplitude, if we're talking about MHV amplitudes, the only object that ever makes an appearance is the Park-Taylor factor, just the MHV tree amplitude. You can dress it with more and more loop integrals. Those are the irrelevant variables. So there's just one object there, very simple. For next MHV amplitudes, there's essentially one object called the R invariant. Really, there's one object, and you just relabel its indices, but it's one function. It's also one object. And that starts first at 5 particles. Okay? For n squared MHV, all the objects you get are exhausted already at 10 particles. Okay? So in general, if you have, in general, if you're talking about n to the k MHV, the formula is that it's at it's exhausted beyond 4k plus 1. 5k, sorry. That's what I meant. Thank you. It's exhausted beyond 5k. Okay? So if you have n bigger than 5k, it's not just that things run out past a given loop order. They even run out past a given number of particles. So if you're doing n squared MHV, you do things up to 10 particles, a fixed number of loops, and then anything beyond that is just relabeling of the objects you have. Okay? But the classification of all these objects, everything that shows up, is what we can now do. Yes. 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 That's right. Yes. You mean, well, yeah. All of those things are about the integrand and these irrelevant variables from that point of view. So the exponentiation definitely has a mirror in the structure of the on-shell diagrams. I can explain it to you later. But again, all the stuff in the loop integrals that we care about a lot from this language are on these irrelevant variables. The fact that they're called irrelevant from this point of view doesn't mean that, I mean, they're irrelevant from the point of view of reducing to these graphs, but this way of organizing is actually very powerful for directly giving you what the loop integrand is. And you can see all the things all those things that you're interested in from studying them. But the actual structures that you have multiplying them are the things that are sitting there at the bottom and are classified in this way. All right, so this story has been purely, yes?
Is the stronger statement in the statement that there are finite number of variables?
Yes, yeah, absolutely.
Information about these RN variables also, the on-shell diagram.
Yeah, so.
There are only 14 n squared MHV, and there are only 127,776 n to the fourth MHV functions. So I mean, for infinite n, you're looking at n to the fourth MHV, only 127,700 something functions ever appear, and it's the same function. For n squared MHV, it's just 14 of them.
Yeah, but really, I mean, the whole thing is just completely classified and understood. For the purpose of time, I'm just talking about the main conceptual points. But there's well, so you saw many of these tables in Jake's talk, for example. Okay. Yes.
Just to clarify, basically, you said at some point that the reduced graph with the smallest number of faces,
Yes.
the number of faces minus 1
Is the dimensionality of the configuration? Yes.
and
Right.
the sort of loop order at which it
No, it has nothing to do with the loop order. That was Ashok's question. It has nothing to do with the actual loop order for the physical amplitude. Okay, it's not nothing, but it's not very directly tied to that. Okay, so I mean something we saw yesterday. See here we're drawing just any particular on-shell diagram, right? Every one of these things has a physical interpretation of some on-shell space process. Okay, some on-shell process. And what we saw last time is that a particular combination of these guys gives you the actual amplitude. Okay? So if you care about the actual amplitude and the actual amplitude alone, you don't care about any one of these things individually. You care about the particular combination which is put together with this, for example, with this all-loop BCFW recursion. Okay? So there's many different sort of parts to the story. But the idea is that there are basic building blocks. There are basic building blocks. These basic building blocks are individual on-shell processes. They can be wonderfully glued together to give you the whole scattering amplitude, but they also have interesting meaning all by themselves. And the the real point here, by the way, is that each one of these objects, as I said yesterday, you should think of them as some form, okay? Some form that you get. They're completely free of infrared divergences, they're completely free of ultraviolet divergences, they're totally well-defined data associated with the theory. And so they should exhibit all the symmetries that the theory has without being obscured by one or other of these problems. So it's these objects all by themselves that are the Yangian invariants. Okay? So that's another mathematical way of talking about these things. I haven't told you how to associate them with functions of external data or anything like that yet, but just skipping to the end, every one of these on-shell diagrams by itself is perfectly invariant under all the symmetries of the theory. And as I mentioned last time, each one by itself is not local. Okay. So the particular way that they're glued together by the recursion relations magically glues these non-local objects together in such a way that the final answer is beautifully local and unitary. Okay? And so understanding how that happens and understanding more invariantly what this particular combination is that gives you the amplitude is then the way of understanding where locality and unitarity are coming from this more primitive starting point. But each one of these things by itself has a meaning. Each one of these things by itself is a particular kind of singularity that you could actually have in the amplitude. And they're the building blocks that see all of the symmetries. Okay, so now what I want to start doing is going back to the on-shell diagrams and actually trying to compute them. So now we're going to start making the connection to the Grassmannian. Okay. And to see, we already saw last time why the Grassmannian might make any appearance at all in thinking about the external data. The external data is a two-plane in n dimensions, it's a lambda 2-plane and a lambda tilde 2-plane that are orthogonal to each other. I now want to see how the Grassmannian also naturally shows up in actually trying to do this computation. Okay? So what's the hard part of doing this calculation? After all, everything looks simple. If we're thinking about these in the usual way, where they're just not using lambdas and lambda tildes and everything like that, you know, what would we do? We'd just say, well, there are delta functions for momentum conservation here that just fix this momentum to be that. Okay? So from this point of view, from the usual point of view, the hard part would be that you put some quadratic constraint that these guys are on shell, right? So L squared is 0, L plus P1 squared is 0, and so on. So that trivializes the internal guys, but the constraint that they're on shell is non-trivial. From our point of view, we're putting them on shell to begin with, so that part is trivial. But it's a momentum conservation in between, which is not non-trivial, because momentum conservation is now this quadratic condition that delta of the sum of lambda lambda tilde has got to be 0. Okay? But like I said before, it can't be as bad as it looks, because we know that the actual configuration, the geometric configuration that satisfies momentum conservation for each one of these vertices is extremely simple, right? However, the way that we represent the amplitude, where we just say it's delta 4 of the sum of lambda lambda tilde, delta 8 of the sum of lambda eta tilde, let's say over 1, 2, 2, 3. Let me do the other one. Let me do the k equals 1, 1. It's even simpler. So if we do the k equals 1 vertex, it was delta 4, the sum of lambda lambda tilde, delta 8, the sum of lambda eta tilde. I did it again, sorry. Delta 4 of 1, 2, eta tilde 3 plus cyclic over 1, 2, 2, 3, 3, 1. I mean, you could say, what could possibly be nicer than this? Well, the one thing this is not making totally clear is that indeed, in this configuration, the lambdas are all proportional to each other. Okay? You have to discover that by looking, solving what it looks like on the support of that delta function. So what we'd like to do is rewrite even this 3-particle amplitude. It still hasn't been given in the optimal form. Rewrite it in a way that makes that fact manifest. And the idea is to actually notice that if this was the lambda tilde plane, in this case it's the lambda tildes that were generic, its perpendicular plane, lambda tilde perp, was exactly this. Its 1, 2 component, its first component is 2, 3, the next one is 3, 1, and the next one is 1, 2. That's what we saw last time is actually orthogonal to this. So this is a little interesting. Notice that the guys that occur on the bottom and the guys that occur inside that fermionic delta function are exactly this orthogonal 1 plane. So the idea is that we're going to do something a little strange. Instead of saying that lambda and lambda tilde directly have this relationship to each other, that they're orthogonal, what we're going to do is introduce an auxiliary object. We're going to introduce a 1 plane in 3 dimensions, okay, so just a line, and we're going to demand that we're going to integrate over configurations of the line and demand that this line contain the lambda plane and be orthogonal to the lambda tilde plane. Okay? So if we do that, you see it's going to force the lambdas to, we're not directly imposing a constraint between the lambda and the lambda tilde, we're introducing a third object and forcing this line to contain lambda and be orthogonal to lambda tilde. Now, just for convenience of writing the formulas, forcing it to contain lambda is the same as forcing its orthogonal complement to be orthogonal to lambda. Right? So what I want to do is integrate over the space of 1 planes in 3 dimensions. So I'm integrating over a little trivial Grassmannian, d1 times 3c. So c will be some c1, c2, c3. Okay? But I'm now going to impose delta functions. First, for the fermionic guy, I'm going to impose that c dot eta tilde is 0. I'm going to impose that c is orthogonal to lambda tilde. Okay? And that c perp is orthogonal to lambda. All right. So these delta functions, I mean, so this is a 1 plane in 3 dimensions. So remember, this has got to be modulo GL1, if I want to describe it like that. And so there's really only 2 variables here. And so, for example, this delta function is exactly nailing C to be this 2 plane. Okay? So this is just nailing C to be that, which if we shove it into the eta tildes is exactly the eta tilde dependence. And if we shove into that is exactly momentum conservation. Okay? We also need to get this denominator. So I'll write that as in a very heavy-handed way, because it'll generalize later, the minors of this 1 by 3 matrix, which are just the entry, the first entry, the second entry, and the third entry. Okay? Now, you also see there's something else very nice about this, because this whole combination is invariant under GL2 transformations. Notice how crucial the fermions are to make it invariant under the G part of GL2. If we didn't have the fermions, it wouldn't be invariant under GL2, because the delta functions would carry weight under the G part, the overall rescaling part. But it's the fermions that fix it. So remember I said that supersymmetry comes up naturally over and over again. From the point of view of the connection to the Grassmannian, it's the most obvious way to be able to talk about K-planes that contain something and being orthogonal to something and so on. If you just write down formulas, the delta functions won't be invariant under G LK transformations, but the fermions just trivially cancel the Jacobians. So that's another way that supersymmetry is forced on you. Okay, so this is already GL2 invariant. This measure has to be GL2 invariant, but the top is not GL2 invariant. If I just had that, I need something with precisely 3 minors downstairs in order to soak up the weight under rescaling C to some constant times C. And so that's why it's very good to have these 3 little minors downstairs. Okay, so this is another way of writing the 3-particle amplitude. It's a little more abstract. We introduced this auxiliary object. But we've now done something very nice. We have made the geometry of momentum conservation totally manifest. And we have completely decoupled lambda and lambda tilde from each other. Okay? So how does it work for the other amplitude? Well, it shouldn't surprise you that it looks like d2 times 3c over GL2. Now it's the minors 1, 2, 2, 3, 3, 1. And it's exactly the same. It's delta 8. So this is a 2 by 3 matrix. So it's delta 8 c dot eta tilde, delta 8 c dot lambda tilde. Sorry, delta 4 c dot lambda tilde. delta 4 of, delta squared c perp dot lambda. Okay? So let's see how this one works now. So now this delta function is just telling you that C is the lambda 2 plane. So now you see I'm integrating over the space of 2 planes where the 2 plane contains lambda and is orthogonal to lambda tilde. Now the lambda plane is generic, so C containing lambda just means C is lambda. Okay? So this forces that C is the lambda 2 plane. Shoving in here gives me the fermionic delta function. That's momentum conservation. And the minors of this matrix become nothing other, because it's just the lambda plane, or nothing other than angle bracket 1, 2, angle bracket 2, 3, angle bracket 3, 1, which is the Park-Taylor factor. Okay? So this is the k equals 1, n equals 3 amplitude, and this is the k equals 2, n equals 3 amplitude, which, following trying to make this picture of the geometry of momentum conservation manifest, we have associated with a little, so with every black vertex, we've associated these auxiliary variables that live in G23, and for every white vertex, we have these auxiliary variables that live in G13. Okay? All right. But now here's the big payoff. The big payoff is that we can trivially perform the integrations over all the internal lines now. Okay? So what's going to happen when we integrate over the internal lines? Integrating over the internal lines is just doing the d squared lambda I, d squared lambda tilde I, d4 eta tilde I for these internal lines over GL1. But now we can use those delta functions independently for lambda and lambda tilde and just nail them. Okay? So what that really means is that associated with every black vertex, let's say, let me use a different notation now. There's a point in G13 given by B1, B2, B3. Oh, sorry. It's a point in G23, which, let me think of it as a 2-dimensional vector B1, a 2-dimensional vector B2, a 2-dimensional vector B3. Here it's in G13. Let me think of it as a 1 by 3 matrix, white 1, white 2, white 3. Okay, but if you have any internal vertices, if we have any internal vertices ABC, let's say, then associated with every black vertex is an equation for the lambda tildes, which is that B1 or BA lambda tilde A plus B lambda tilde B plus BC lambda tilde C equals 0. And associated with every white vertex is WA lambda tilde A plus WB lambda tilde B plus WC lambda tilde C equals 0. So now that you give me a graph, it's associated with a whole ton of linear equations. 2 linear equations for every black vertex, and 1 linear equation for every white vertex. Okay? Now all we have to do is eliminate lambda tilde I from those equations. So if we eliminate them, what we're left with is some linear relation between the remaining lambda tildes, which are the external ones. Okay? I keep misplacing this. Okay? So you just eliminate the internal guys. Now, how many equations am I going to have? So here I had 2 equations for every black vertex, 1 equation for every white vertex, and I'm going to eliminate the internal ones. Okay? So this is the number of linear equations I'm going to have left. Let's call that k. That's exactly the k of the graph as well. Okay? So it's precisely what you'd get from the number of eta tildes counting. Okay? So you have that many equations left. And so let's just group those equations into some just k equations. So I can write them as some c alpha a lambda tilde a equals 0. For alpha goes from 1 to k, okay, and a is going from 1 to n. The c, of course, depends. I have to tell you how to eliminate all these guys, but there's some way of doing it. So the c depends on the blacks and the whites, the little coordinates associated with each one of these guys. Okay? But other than that, there's just k linear equations between the external guys. Right? So what we've done by writing down these equations and eliminating these guys, or ultimately what we've done by drawing one of these pictures with black and white vertices, is we've taken a whole bunch of little G13s and G23s, the most trivial Grassmannians, and we've glued them together to build a point in a bigger Grassmannian, GKN. Okay? So this process of taking little ones and gluing them together into bigger ones is what was naturally done by Fock and Goncharov back when they started working on this thing in the 2000s, and they call this process amalgamation. So it's like you take a bunch of little guys and you amalgamate them together into a point in GKN. Right? So it's clear that this is giving us a point in GKN. Obviously, any k by k linear transformation of these equations are the same equations. So that's why we get a point in GKN. So we need to learn how that amalgamation works. I mean, how to explicitly get that point. But let's now see what this on-shell form is that we get at the end of all this.
So, but also the integration measure over all these little c's becomes an integration measure over the GKN?
Yes, of course. I mean, it defines an integration measure over the GKN.
GKN
Yeah.
seems to have more symmetry than the individual.
Yes. So I'll come to that in a second. Okay, that is a very interesting question. But it's giving you a form on GKN. When you say an integration measure, you're talking about a top form. This is some lower form on a GKN. The interesting question is there a top form on GKN that contains all these guys as its residues? And the answer is yes, and that's the form that we wrote down 3 years ago. Okay, so, I'll come to all that in a second. Okay, but what we have right now is an integral over this measure for the white vertices, the measure for the black vertices. We still haven't fixed the GL1s for all the internal edges. Okay, what are these incredibly simple measures that we had with those? Okay, so we have that, and we have a delta 4k of this amalgamated point dot eta tilde, delta 2k, the amalgamated point dot lambda tilde. Now, I didn't write down, there's also the equations for the lambdas involving the C perps. But what do you think it's going to do here? It's just exactly the same thing with k replaced by n minus k and c replaced by C perp. Okay? So that is what we've now replaced the on-shell diagrams with. The lambdas are gone. We're just integrating over these little G13s and G23s. And notice that those measures, that they're not complicated. They're just d log of variables trivially, right? Each one of them just has 2 degrees of freedom. So if I just skip ahead for a second, there's a symmetry between G13 and G23. So the measure on G13 is just like, for instance, I can gauge fix a set C1 to 1, and then it's just DC2 over C2, DC3 over C3. Or you'd really write it as DC1 over C1, DC2 over C2, mod GL1. Okay? But it's just d log of all these coordinates. Okay? So we have a whole bunch, we have 2 variables associated with each vertex. the measure is just a d log of those variables. And so the measure is trivial. It's just a bunch of d logs. All of the interesting stuff has now gone into how you amalgamate them into that c. That c is going to depend on some very interesting sort of polynomial way on these little coordinates, because which comes from telling you how to solve those equations. Okay.
And is this manifestly invariant under those moves?
Yes, yes, absolutely. I'm going to come to that just right now. Okay. Yes, it's manifestly invariant under the moves. Yes. Yes. No. There is actually, and it will not be more than. I'll stop before 1. Okay. Okay. Yeah, there really is a natural place. Okay. So, but by the way, I also hope you see something here that this transition from the actual on-shell diagram to the Grassmannian, what motivated is just the geometry of 3-point momentum conservation. And that means that you could do the same thing for any theory. Okay? It's a convenient way of doing the intermediate lambda integrations. For any theory, it didn't have to be planar. None of that came in here. Okay? You would just write down linear equations for the black and white vertices. And for every theory, you will get the same C. Okay? So the same structure in the Grassmannian is built out of any theory. What's special about n equals 4 super Yang-Mills was how simple the measure is out in front. Okay? So the measure is just d logs, d log of all of these coordinates. But the connection between on-shell diagrams and the Grassmannian is much more fundamental than that. Okay. Okay, so I now want to just tell you a few more basic things about this, and then maybe in the discussion tomorrow I can say a little bit more. Okay, so at the moment it seems like the variables are associated with the vertices. Of course, there are all these GL1s of the internal guides that we haven't modded out by yet. Okay, so in fact it's easy to see that that really the variables are associated with the faces of the graph. It's easy to see even purely geometrically. Let me not for the moment give you the most invariant geometric way of thinking about it. I'll give you a concrete formula instead. But before doing anything else, let's just do some counting. The number of variables we have is 2nv minus the number of internal edges. That's the number of variables we have left after we mod out by the GL1s. Okay? But if we use the fact that it's a trivalent graph, so that 3nv is equal to 2ni, and if we use Euler, which, because these things, when they're drawn on a disk, then this is trivially equal to nf minus 1. Okay? So the actual number of degrees of freedom is the number of faces minus 1, which strongly suggests that, in fact, the real variables are associated with the faces. Okay? So, as I said, we can say it very geometrically, but let me actually skip ahead and say it more practically directly here. So what we're going to do is actually gauge fix the G13s and the G23s in a natural way to actually explicitly eliminate all the internal lambda tilde. So I write down a concrete formula for you. Now, since it's a gauge fixing, it's going to introduce some arbitrariness that's not actually there in the actual answer. So the fundamental, you remember, the 3-point vertices don't have, they're just that. Okay? But we're now going to give them some orientation. Okay? So I'm going to put an orientation where the white vertex has 1 in and 2 out, and the black vertex has 2 in and 1 out. Okay? Actually, if we were doing a non-supersymmetric theory, we would be forced to give them orientations anyway, because we have to give helicity information. Okay? And the orientations would give helicity information. Here, in n equals 4, we exactly don't have to do that, but I'm going to use this to do a convenient gauge fixing. So remember, this white vertex is associated with one equation. So if this is, I don't know, 1, 2, 3, the way I'm going to write down that one equation is let me write it like this, is x1 lambda tilde 1 is equal to x2 lambda tilde 2 plus x3 lambda tilde 3. Okay? So in the general form, that's like putting a minus sign. If I was thinking of it as a 1 by 3 matrix, it's like writing it minus x1, x2, x3. And the two equations associated with the black vertex, I'm going to write down. So these are the three variables mod GL1. And here, this guy had a GL2. It's going to be convenient to leave a GL1 left over so it looks just like this. So let me call these variables y's. Okay? So here I'm going to write down the equation y1 lambda tilde 1 equals y2 lambda tilde 2 equals y3 lambda tilde 3. Those are the two equations for that one. Okay?
So these are the B's and the W's.
These are the B's and the W's. All I'm doing is putting judicious minus signs and gauge fixing the B's. Right.
So you went
Yeah.
from the B being a 2 vector?
Yes. So for instance, I can use the one thing that you can always do is gauge fix so that it looks like 1001 xy. Okay. Right. So I fix it like that. So the equations are this equals that, that equals that. I just reintroduce the GL1 to write it a little more symmetrically like that. Okay. Okay, but you see now the advantage of writing it like this is that each one of these guys is charged under a GL1 attached to the vertex. Okay? And now there's an extremely simple formula for eliminating all the internal variables. Okay? The reason is that, so what I now have to do though is I have to take the graph and I have to be able to orient it in this way. Okay? So, it's not 100% obvious, but you can show that every graph can be given an orientation like this. That's called the perfect orientation. Okay? So if you take any graph, it can be given a perfect orientation. Actually, that's not quite true. There are very simple graphs you can draw that don't have a perfect orientation. But that comes from only one class of diagrams. The diagrams that cannot be given a perfect orientation are the ones where in a subgraph, the effective k is less than or equal to 0, and the dual and the white-black dual statement. Those are exactly the diagrams that just vanish under fermionic integration for us anyway. Okay, so the diagrams that are not 0 can always be given a perfect orientation. So if I give a slightly non-trivial example. So here I have it's like 1 in, 2 out. Okay, so let me do 1 in. So this is 2 out, 1 in, 1 in, 2 out, 2 in, 1 out, 1 in, 2 out, 2 in, 1 out, 1 in, 2 out. Okay, so that is a perfect orientation of that graph. Okay, so I take the graph and I now give it a perfect orientation. Now here's the formula for what the linear relationship between all the external guys is. You think about all the incoming lines as sources and the outgoing lines as sinks. Okay? So I'm going to give you a formula for the lambda tildes of the lambda tildes of the incoming lines as some linear combination of the lambda tildes of the outgoing lines. Put a minus sign there so we can write that like that. Okay? But what is this minus Cij? Okay? Okay. Let me say one more thing before I tell you what minus Cij is. You see, here I have lots of internal variables. They're attached to the vertices. So there's the internal variable here and the internal variable there. However, because I'm integrating this guy out, because I'm just eliminating them, nothing on the outside can depend on the GL1 weights of the internal guys. So the only combination of these variables that can enter is the ratio of the weight on one side and on the other side. That's just as a consequence of the GL1 invariance with respect to each vertex, right? In fact, we have a GL1 associated with all the vertices, so that's just as if we have a GL1 lattice gauge theory. And so the only kind of relationship that can be between this guy and that guy is something that involves a product of the links along the path. Okay? So what you really have are, even though the variables start off associated with the edges, with the vertices, they only occur in combinations, and after you mod out by the GL1, that's the only combinations you get, which are associated with the edges of this graph. Okay? In terms of these x's are just the ratios of the variables on one end and the other. So now I have variables that I associate with the edges of the graph. Okay? And now Cij is nothing other than the sum over all the paths from I to j. Paths now according to this perfect orientation, not left-right paths. So, you know, if I want to go from here to there, that's one path that I could take. There could in general be many paths. It's just the sum of all the paths from I to j of the product of all the edges of the edge variables along the path. That's an explicit formula for eliminating all the internal variables. Now, in this description, the edge variables are still charged under the, what we're talking about before are the GL1s of the intermediate lambda tildes. These guys are still charged under the GL1s of the vertices that they touch. So this is still got some redundancy. And so the only things that show up here are actually the fluxes around the faces. Okay? And so those are the, so that's the most invariant description. So I can give a perfect orientation. I can put these edge variables on there. But only the gauge invariant combinations show up. The gauge invariant combinations are exactly the ones that are the product around the faces. Okay? Oh yeah, no, the edge variables are a ratio of the x and the y. Okay? Yeah, so if you had an x here and a y there, the edge variable would be x over y. Okay? So exactly the one which is indicated by the arrows.
But you say that finally
Right.
it will depend
Yeah.
only on something.
Finally, it'll only depend on the actual flux. Exactly. Okay? And this we see, I mean you see just following your nose very, very directly. But now we're really done. Now we're giving you an explicit formula for any on-shell graph. Okay? Oh, and of course, the product of all the face variables is equal to 1. Okay? So that's why the number of independent variables is the number of faces minus 1. Okay? But we've seen now that starting from any on-shell diagram, there's associated with it a form. The form, I'll write the integral sign, but it's a form, it's a product, in this presentation, it's a product of all the edges, the edge over edge, that's the measure. In this way of doing it, there's still a mod, the GL1 on all the vertices. Okay. And, well, the rest is what we wrote. It's delta 4, C dot eta tilde, delta 2k, c dot lambda tilde, delta 2n minus k, c dot lambda. Okay? Where C is a matrix, I've told you what the matrix is. Okay? That just it tells you exactly what the matrix is. In fact, in this form, this is one of those canonical gauge fixings of the Grassmannian that we talked about. The sources are gauge fixed to an identity block. And the remaining k times n minus k variables are exactly these ones. Okay? So I've told you precisely how from the edge variables to build the corresponding point in the Grassmannian. And I can, of course, also write this as a product over the faces, d face over face, all the faces but 1, because the product is 1, and all exactly the same thing. In terms of the faces, what is this formula? In terms of the faces, it's that, I'll just erase it here, it's the product, it's a sum of all the paths from I to j, and it's the product of all the faces to the left of the path. Okay. Yeah, just Stokes theorem. Right? So this is the completely invariant way of writing it. But the edge variables are often much more convenient to think about. Okay, so we've seen now that we go from an on-shell graph is naturally associated with a form on the Grassmannian. Okay? And not only have we found a form, we found a particularly nice set of coordinates to describe the form. The measure is just d logs, but I've built the matrix in this interesting way. All right? Okay, so, so at this point, it is trivial to see that the merge on merge and the square move and so on are invariances here. Why is it trivial to see? Well, but it's not just that it's trivial to see, we also learn a little bit more. Okay. So, for instance, why is it that this and that should be the same as each other? Well, now it's completely clear. Both of these things are just giving you a completely generic top dimensional configuration on G24. So there must be some change of variables that takes you from one to the other. Okay? So all you do is but now I have to give you a mapping between the edge variables or the face variables. Okay? So you just have to make sure that the point in G24 that you make from this picture is the same as the point in G24 that you make in that picture, but it's obvious that it must be possible because they're both giving you generic points in G24. So let me tell you what the formula ends up being. So if that face variable is F1, F0, F1, F2, F3, F4. So the product of all of them is 1. There's a constraint that the product of all of them is 1, but let me just write it like this. Then if you just do this, it's a very straightforward exercise, you find the following beautiful transformation. Okay. So now we see more than just combinatorics. Now there's an actual change of variable. Okay? This transformation is famous in this kind of business, and it shows up all over the place in a whole variety of settings, as does the square move. This is known as the cluster transformation. And this whole subject, there's a whole subject of cluster varieties and so on, of which the positive Grassmannian is a special case. But anyway, you don't need to, I'm just telling you the name in case you hear it. We don't need to know anything about this, which is good, because I don't know very much about it. Okay? But there's something very important about this transformation, which is that it leaves the form d log, d log, d log invariant. Okay? So the form d log, d log, d log is obviously invariant into this, because everyone is just rescaled in some trivial way by F0. Okay? So the d log, d log, d log, d log of everyone is invariant. Okay? The measure is invariant. I kept telling you that these merge on merge is a much more trivial move, and why is that? It's because in this case, the face variables are just staying the same, right? I mean, that's the point. It's F1, F2, F3, F4. This goes to F1, F2, F3, F4. Okay, so the face variables totally stay the same. Okay, but we can also see reduction here. Because again, obviously, this and that are just giving you a point in G12. Very trivially, they have to be the same. But now we seem to be losing a variable. So what is the rule? So it's F1, F0, F2. If this is that one, then just by finding what the point is in G12 and making sure it's the same, this is F1 times 1 plus F0. This is F2, F0 over 1 plus F0. And F0 is gone now. Right? So that's the sense in which F0 is an irrelevant variable. You can completely reabsorb the importance of f naught and just redefining what the other variables are. Okay? And now it doesn't play any more a role in determining the point in the Grassmannian. Of course, the measure is also invariant. So if I call these things f1 prime and f2 prime, then it's true that the original measure, which was d log f naught, d log f1, d log f2, this is now going to d log f naught, d log f1 prime, d log f2 prime. Right? But this is the sense in which this is an irrelevant variable. Nothing else depends on f naught now. I've completely isolated I've removed all the dependence on f naught in doing this change of variable. So f naught just sits on the outside now. Now you can do whatever you want with it. If you're computing residues with these graphs, leading singularities or what were called composite leading singularities, although all these things are treated in a completely uniform way, so we don't have to make any artificial distinctions. If I'm taking residues, by the way, finding singularities of these forms are completely trivial. It's just where edge variables are sent to 0. There's all these d-log doing the square moves to isolate a bubble. Then what's going on is, as I go along, all the variables are changing under these cluster transformations. And then, aha, I find the bubble. Then I isolate that guy. Say, oh, great, the d-log of that variable is coming out in front. Then I keep going. I isolate the next one. I send them all to the side. So I have d-log of 4 variables sitting there. The variables, the arguments are all functions of the original variables that I started with. And by the rule that I told you about how to associate L with the lambdas and the lambda tildes, I can then translate that association to telling me the map between all these irrelevant variables that have been shoved to the side and the original loop momentum. Okay? But the point is that they're truly these irrelevant variables in this case. Now, I haven't described this k-plane in n dimensions in a more geometric way, but you can really think about everything that is going on here as actually projecting from a very, very large Grassmannian down to a low one. And the loops are really the variables of the projection in this set. Okay. Okay, so I will leave it at that. But let me just say a few things that I might mention tomorrow if there's time, because I have not remotely closed the chain of connections here yet. Okay, but so yesterday on-shell diagrams are interesting. We see that the invariant content of on-shell diagrams just graphically is captured by these permutations. Okay? But we see that the on-shell diagrams are actually also associated naturally with a structure in the Grassmannian. Okay? And again, notice, coming back to Ashok's question, nowhere here does the 4-dimensionality matter. Nowhere either in the structure in C or in the measure does the 4-dimensionality matter. The only place 4 comes in is in this thing that these delta function constraints that ultimately tell you that this k-plane, I should have said that, those final delta function constraints, which is the only place the external data enters. It enters in these delta 2k c dot lambda tilde delta 2n minus k c dot eta tilde delta 4k c dot eta tilde. This is the only place the external data makes an appearance. That's the only place 4 makes an appearance. Okay? But what is this thing telling you geometrically? This thing is telling you geometrically that the k-plane C contains lambda and is orthogonal to lambda tilde. Okay? So it's really the requirement that the k-plane that you built from this amalgamation procedure contains lambda and is orthogonal to lambda tilde that converts all the structure to finally some function of the external data. So we have 3 levels of structure: purely combinatorial in the graph, an associated structure in the Grassmannian, and finally, by this process, a window into the structure converts all of this into some actual function of the lambdas and lambda tildes. I should say that just one more thing. One thing which is made obvious, it's not totally obvious in this presentation, but if you Fourier transform this into twistor space, you find that just this dependence on external data turns into the beautiful object, just delta 4/4 c dot the super twistor variables. Okay? That's a 2-line derivation that shows that this in momentum space Fourier transforms to that in twistor space. And this makes it obvious that what we're talking about is superconformal invariant. It makes an SL4/4 symmetry completely obvious. Okay? So that's good. The totally obvious symmetry is, of course, obvious. Okay? All right. But other than that, anyway, this is the only place where the external data enters. So to complete the picture now we have to understand what is the meaning of this permutation. The thing that we just got purely graphically, the invariant data, now we've associated with the structure in the Grassmannian. So what is the meaning of that permutation? And it turns out that with one of these graphs, when you draw one of these graphs, this k by n matrix that you build, this point in the Grassmannian that you build, turns out to be very special. Of course, it has to have some special property. To understand its special property, we have to return to thinking about these k by n matrices not as k n-dimensional row vectors, which gives a plane, but vertically as n k-dimensional vectors. Okay? So we think about it as n. So it's a configuration of vectors in a k-dimensional space modulo GLK. Okay? So we have these columns. Okay? So it turns out that there's some very special relationship between these columns, and the relationship between the columns is that they are characterized by linear relationships that they satisfy between chains of consecutive vectors. So in other words, you might have a completely generic configuration where the vectors are all independent of each other, but then you might have a configuration where vector 3 is a linear combination of vector 2 and 1. That's a one more special configuration. Okay? So anything that puts linear relationships between consecutive guys puts more and more constraints, makes more and more special configurations. It provides a so-called stratification of the Grassmannian. Now, if you didn't have this criterion that we only care about consecutive linear relationships, the general problem of trying to stratify the space of configurations of vectors in n dimensions is known to be a very difficult problem. Okay? And in fact, it's a problem with no known solution. Anyway, it's a very, very difficult problem. But remarkably, this one little extra structure of having consecutive dependencies gives a very beautiful stratification. And it turns out, even though it isn't totally obvious, but if you want to classify chains of consecutive vectors and the kind of linear relationships they have, it turns out that they're completely fixed by giving a permutation. Okay? And the permutation is exactly the permutation that you read off from the graph. So you take the graph, it gives you the structure in the Grassmannian. The special thing about that structure is it's a part of the cell decomposition of the Grassmannian according to this stratification. And it tells you exactly what linear relationships between the vectors you actually get. And it's that linear relationship which is the completely invariant data. Okay? And there's this form on any one of these strata, which is just this nice D-log form. If all the variables are real, on top of it, it turns out that the part of the Grassmannian that you're painting has a very special property. And it's known to be inside the positive Grassmannian. The positive Grassmannian is a generalization of the simple idea of a simplex. So if you have a little triangle, then we can draw 3 lines on a projective plane who can be inside a triangle. But a way of specifying what the inside means is to choose coordinates x1, x2, x3, and say that all the coordinates are positive. If you want to generalize that notion to the Grassmannian, you have to fix some order 1, 2, 3 up to n, and declare that all the minors of the Grassmannian are positive. Okay? In that ordering, all the minors are positive. That turns out to be a much, much richer space. In order to find its boundaries, for example, you can't just set one variable to 0 at a time like you can for a simplex, because they satisfy nonlinear relationships. And so when all these variables are real, this is actually painting a part of the positive Grassmannian. And thinking in that way, from a variety of points of view, exposes as a trivial symmetry of that space just diffeomorphisms that preserve the positivity, and there are even simpler ways of thinking about it. That immediately exposes the second SL4/4 symmetry, and in fact the full Yangian symmetry of the theory. Okay. So maybe that and a few other things I will talk about tomorrow if there's time in the discussion. Okay, thanks.